So what is the potential difference between these 2 points? So I have a charge that sits right here. And then I have 2 points in space that are at 5 centimeters and at 10 5 centimeters, right? 5 over, 5 up, 10 over, 5 up. Those are those 2 points in space. And what I want to know is, what is the potential difference between those 2 points? And so what you have to do is you have to calculate, we'll call this V2, and it's going to be equal to K times Q divided by R2. And then here we want to calculate this potential, which is going to be, I'll call this V1, is going to be K times Q over R1, KQ over R. We've been doing that, except the only difference here is that we had 2 points in space and we want to know the potential difference between them. So like for example, let's just do V2. V2 is 9 times 10 to the 9th. Q is 20 times 10 to the minus 9 coulombs. I have to convert it to coulombs from nanocoulombs. And now R, and this is probably where you got stuck, because a lot of people took this distance, but that's not right. That's not the distance that you want. You want to know the distance to this charge, which is at the origin. Right? The charge is at the origin. And that distance, well, this is 5, this is 5, so it's going to be the square root of 50, so 7 point something. The square root of 5 squared plus 5 squared. Yeah, 7.1 divided by 7.1, excuse me, 0.71, because it's 0.71 meters. It comes out as, no, 0.071, because it comes out as 7.1 centimeters. And then convert that to meters, and that's not squared. And then that gives you some value for V2. I'm not sure what it is. Does anybody know right off? Do y'all know what it is? You don't have to calculate it, but you calculate that value for V2, and then you do the same. This is bright. These are new projectors. Have y'all noticed? This one used to have the light bulb is about to go out sign. You have red class in here? It's your tech fees at work. So you calculate this V2, and then you calculate this V1, and then just take the difference between them. V2 is going to be the bigger of the two because you're closer to the charge. R is small, so that V2 is bigger. Is it okay to forego those calculations? All right. What else, y'all? That's a good question. Potential difference is kind of an important idea because we'll use it in circuits next chapter. What else? One? Yeah, that's another good one. I get this. All right, so number one, we had this proton that was going between these equipotential lines. It was moving from, where's point B? I don't think I'm seeing the full figure here. The point B, I think, was at minus 100 volts. Am I right about that? Oh, okay. All right. So I'm going from point B to point C. So I have a proton. I'll draw in B right here. This is correct at 500. So I have a proton that's going from here, and then it's going down to minus 100 volts. Now remember, protons move from high to low potential. So this proton is going to speed up as it goes to that minus 100 volts. So our change in potential is going to be 600 volts, because I'm going from 500 to negative 100 volts. So it's not 400, it's not it's 600 volts, because I'm going 500 to negative. I go to 500 to 0, and then I go another 100 volts. So my change in potential is 600 volts. And then I want to know what is the speed. Well, remember, potential is energy per charge. So what I want to do is find that energy. That's going to be all kinetic energy, and set that equal to 1/2 mv squared. So kinetic energy is equal to Q times delta V. all I'm doing there is I'm cross multiplying to get Q times delta V. 600, or rather Q is, it's a proton, so it's 1.6 times 10 to the minus 19 coulombs times delta V, which is 600 volts. And that gives me my energy, whatever that is. And then I set that equal to 1/2 mv squared. I know the mass because it's a proton. It's given here. But on the test, I won't give that to you in the problems. You just need to know, oh, this is a proton. I know its mass and its charge. All right? I forget who asked that. Who asked this question? Abby, is that okay to stop there? Because once you go here, you get this number, and then you solve for V. And then that's the answer.
I have a question.
What's up?
Not really, just so the charge of a proton in this example is different from, like, I'm going to just say for homework number 1, number 4, so that you can look at it.
On this one?
No, homework, the first one. This was
Oh, okay. All right.
I can't answer, but it tells me to use a different number for the charge of a proton, and that's what I'm
No, it doesn't tell you that. All right, let's look at homework number 1.
Yeah. See, it says use 1.6 times 10 to the negative 9. Then this says times 10 to the negative 19.
Number what? 4?
Yes.
Oh, so in this one, you want to know how many protons make up 1 nanocoulomb of charge. A nanocoulomb of charge, that's a whole bunch of protons, right? One proton has a charge of 1.6 times 10 to the minus 19 coulombs. This is one proton. The E plus is a proton. So I want to know if I have 1 nanocoulomb, that's 1 times 10 to the minus 9th coulombs, how many protons is that? And so I divide that by 1.6 times 10 to the minus 9 coulombs. Right, this is my big bunch of protons, and this is a single proton. And I want to know how many protons are in this, so I divide it by the single proton charge. Yeah. Yes, you're right. Negative 19. Thank you. And that's why it's, 6 times 10 to the 9th. Alrighty? Alright. What else, yeah? I'll be thinking. I'm going to erase this. Either open. Okay. Shoot.
For the next one,
Okay.
I got, mine's just off calculating myself. So I got 1.2 times 10 to the negative 8.
I don't know what you did. We can look at it, but you will have some like this, and hopefully, I want everybody to get these. I want everybody to get every question, honestly. But these, y'all should get these because they're fairly straightforward. Now, you know what you might have done is that you might not have converted this 3 centimeters properly. So let me just show you quickly. The force is kQq over r squared. This is 9 times 10 to the 9th. Q is 4 times 10 to the minus 9 and 3 times 10 to the minus 9. Those are my 2 charges.
So it wouldn't be, you don't carry out the negative.
No, you don't carry the negative. In fact, on your equation sheet, there are absolute value bars around those Q values. And because this is a vector quantity, you don't carry the negative because your negative is wrapped up when you draw the vector. And then this is divided by 0.03 meters squared. Yeah, it was probably...
I didn't convert it, and I tried the negative one.
Okay. All right. What else, y'all? I can erase all this. Okay. What else? Want me to pull up an exam and we'll just sort of peruse it? All right, let's do that. Huh? The hard ones. Well, they're all easy if you know how to do them. Huh? I don't know them off the top of my head, but yeah, I have that information. Do you want me to send it to you? The most missed problem? Okay. As I told you, you're going to have a figure that looks a lot like this figure. It won't be the same charges or the same distances likely, but I'll ask you to find the forces and the fields and the potential. On this one, a student asked me about this. This one was asking for the magnitude of the force on the 5 nanocoulomb charge. You realize that the magnitude of the force, that there's only one force that acts on that charge, right? Because there's only one other charge. And that force is just from Coulomb's law. F equals K QQ over R squared. What is R going to be for this particular problem? It's going to be 5. Very good. It's just the distance between the charges. But remember, if I'm looking instead for, say, the electric field at this point, then I have to use these distances because I'm looking for an electric field. No, there's no charge here, right? But I still have an electric field at this point due to these two charges. So fields can exist just out in space without any other charges present. I mean, you have to have charges somewhere else, but they can exist in a point where there is no charge. The same is true for potential. However, forces cannot. A force has to act upon a charge. There's a force acting on this charge and a force acting on this charge. It's sometimes hard to keep those things straight in your mind. Forces and fields and potential energy. I think it's hard. What else? Any of these stand out to you people? Potential is energy per charge. Potential energy is the energy of a configuration of charges. You can only have potential energy with 2 or more charges. Because if I just have a single charge sitting in space, there are no forces acting on it. So it has no potential energy at all. That's why in potential energy, when you're calculating it, is KQQ over R, right? Because you have to have 2 charges to have potential energy. But with potential, you can have an energy per unit charge. It's kind of like with the fields, that I can have a potential out in space. Like I can say, calculate the potential at this point right here, and that has a meaning to me. I don't have to have a charge at that point. In fact, if I did have a charge at that point, that charge would not contribute to the potential at all. Okay? All right. Does that answer your question? Whatever.
Well, you think it's in the homework in the workbook, but it's number 2 from the first chapter.
From the what chapter?
First.
Okay. These are online, by the way, the homework. You have it in your workbook, but I have the problems if you want to print them out, and then also solutions to them. We're looking at chapter 2? Chapter 1. Okay, first of all, we worked a problem like this in class, and you're not going to have one that's the same difficulty as this. You'll not have a force problem with 3 charges. Do you hear me? But you will have one with 2 charges that will have forces in 2 dimensions. So I don't want to step through all the different vector business, but let me just lay out the vectors for you. Is that okay? Or did you have a specific question about it?
No, I already did it. I just didn't know if we were going to have one on the test with 3 charges.
Oh, no.
So will we have one? Can we do one that we would have on the test?
For forces? Yeah. In fact, actually, usually when I give you a 2D problem, it has to do with fields and not forces, because it's
So
just...
we're not going to have one that we have to break up in X and Y, or we will?
You will have one that has X and Y components, and you'll have to find the resultant. For example, let me show you on this problem. I'm sorry, I cut you off. What were you going to say?
So we won't have one where we have to find the sine and cosine of the results.
All right. But for example, here, if I want to know the electric field in this direction would be like that, and then the electric field in this direction would be like that. And then you would have to find those magnitudes, and then find the resultant, and find the angle. So you have to work with vectors, but no, you're not going to have to do something like in that problem. We did one of those in class, and I told you when we did them that, this was more complicated than you'll see on the test. It's just details, really, right?
Almost like the one you went over in the very beginning, and you were like, I'm gonna ask you this problem, and then this question, and then.
Yeah, that's right. Okay? All right, what else? Y'all get these things? We didn't spend a whole heck of a lot of time in class. Y'all understand these things where the potential is 0? Let me just show you quickly. Here I want to know where is the potential equal to 0, because this one's a little bit different than the one we had in class that we did. I want to know where along this line is the potential equal to 0. Does anybody want to take a gander? B is right. B? Yeah, B is right. B is the only place on this line. The one we did in class, I think, the entire line had a potential equal to 0. But here, B is equal to 0, only B, because at B, I got equidistances between these 2 points, so the potentials of those charges cancel out, and these 2 points. But notice how the 1 and the -1 charges are shifted across, and the 2 and -2 are like that. If I look at point D, for example, the distance to this charge is different from the distance to that charge, so those potentials don't cancel out. And then similarly, these distances are different too, and so those potentials are not going to cancel out. And so my net potential is going to be something other than 0. I don't know right off if it's going to be positive or negative, but I know that it's not going to be 0. Only at point B do I have a potential equal to 0, because the potential of those charges will cancel out. This good? Okay, 22? I understand.
So my question is, electric potential is going to a force, right?
But it's not a force, so what's the answer? 1 and 3 are conservative forces. Yeah, that's an okay question. We talked about conservative forces early on. Remember, conservative forces are field forces. Electric forces, gravitational forces. Those are really the only conservative forces that we're concerned with. There's a potential. Finding the potential of those 3 charges, y'all can do that. You'll have to do it on the test. Y'all can find the potential of 3 charges. It's a scalar quantity, remember, so you're calculating V equal KQ over R, kind of like we did with that OpenStax question. In this one, the tricky part is finding this distance, which is, the square root of 1 squared plus 1 squared. These distances are 1 meter, 1 meter. So you'll have 3 contributions to the potential. Oh, but look, the good news is on this one is that these 2 charges, their potentials cancel out. So really, you're just dealing with this charge. Look for those. I try to make problems as simple as possible. I try to make little tricks like that when you start working them, that the math works out easily. It's not always the case, but I try to make that the case. Because, I'm not testing your algebra, I'm testing your physics. All right, what else? Any other tests? I can pull up others. This was spring 15, but I got them all. Oh, now y'all usually have more questions than this.
For number 4 on this test.
Okay.
So is that little wire ever going to spin?
Yeah, it spins.
It does?
Mhm.
What are the circumstances that would make it spin?
This is the circumstance. Because if I bring the negative rod up next to the wire, sorry, I usually do this in class. I usually bring it, but I just forgot this semester. Just a little piece of copper wire. I take a piece of PVC pipe, I rub a wool sock on it, and I get negative charges on it right here. When you do that, you get, you get all your negative charges over here and your positive charges over here, and you can just pull the little wire around. It'll spin around in a circle, and then you can make it spin the other way around. I mean, it's not like a pinwheel or anything. It goes really slowly. Yeah, as you move the rod, it's like it trails along behind you. It's kind of cool, actually. Okay, what else?
Well,
Yeah,
so
Devon?
as soon as you touch the rod to, like, you touch them, it would stop moving, right?
Yeah, because, well, one, you're touching the wire, but then you're transferring charges onto it. They neutralize. Yeah.
I can go to spring 17, example 1.
Yeah, I'm asking on it. Spring 17.
Number 17.
Sorry, it sometimes gets slow. Number 17. All right. Oh, okay. That's a good question. So, I have these three charges, and I want to know what is the net electric field. So with an electric field, I imagine that I have a positive test charge in the middle. Positive test charge, and then I ask myself, what is the direction of the electric field at that point, which is the direction of the force that that positive test charge will feel. There's not a real charge there, right? The electric field there exists without the imaginary test charge. We just use this imaginary test charge to sample the electric field, to sort of think about it. And so due to this positive charge up here, it's going to feel a force down and in that direction. Or the electric field is down and in that direction. Due to this negative charge right here, it's going to feel an electric field in this direction. And due to this charge over here, it's going to feel an electric field in that direction. And so the net electric field is going to be in that direction. So that's going to be quadrant 4. So again, what I did there is I have three electric fields. I imagine my positive test charge here. Ask myself, what is the direction of the force on the positive test charge due to this charge? It's repulsive, it's down. What is it due to this charge? It's repulsive, so it's to the right. And what is it due to this charge, the minus 3q? It's an attractive force, so it's also to the right. So I got two vectors here, one vector there. The resultant vector has to be in quadrant 4, somewhere in quadrant 4. Okay? And you will see questions like this. It might not be exactly like this, but you will see questions where you have to find the rough direction of the electric field, or the electric force, too. We've done some like that. In fact, there's probably one on here, if I'm not mistaken. Oh yeah, like this one right here. What are the charges on A and C in order to get a force on B that's in that direction? Well, the only way to get vectors that are in that direction is I have one vector that's down and then one vector that's like that. Those two vectors would give me that resultant vector. And if B is negative, that means A is also negative and C is positive, because I have a repulsive force with A and attractive force with C.
Also, for questions like that, electric field and electric force go hand in hand. Like, is that also what you would draw for the electric field?
Not in this case, because B is actually a negative charge.
Okay, so if you have to draw the field of that particular particle first and then figure out directions.
Can you just say those words again?
Like, I would draw what just be with that particle, and I would draw the direction of the electric field based on it being negative.
No. I don't know if I'm understanding you
Well,
right.
to figure out the electric field could be.
If you wanted to find, well, at point B, right, we don't think about the electric field due to charge B at B, because it doesn't really make sense to think about that. But the electric field at point B, you would think about it a little differently. Now, there's no charge there, but the electric field would be in this direction due to A, and in this direction due to C. Because I imagine that B is a positive charge. And so the electric field here would be in this direction because, well, a positive charge would feel an attractive force. A positive charge here due to this charge would feel a repulsive force. So these two vectors represent the electric field due to these two charges. Notice that these vectors are exactly the opposite of the vectors that we drew before. Right? And that's because this charge is negative, actually. It's not positive, it's a negative charge. Does that clear it up or just make it muddier?
I don't know.
It's kind of difficult, isn't it? The fields and the forces, it's hard to disentangle those in your mind.
So, like, B is positive, let's just say it's positive. It doesn't automatically have an electrical field that goes away from it since it's a positive particle.
It does, but at the point where B is, the electric field is infinity, right? Because R goes to 0, and so we didn't really talk about that. In fact, we don't think about our imaginary test charge having an electric field at all. It's just a little tool. It's imaginary. It's not even real. You know, it's not a real charge. It's imaginary. You're just thinking about it. You're using it to help you think about the electric field. Sorry, y'all been thinking it's a real charge, right? Carrying a real charge around in your pocket, it's going to zap you in the bottom. Okay, what else? You're not going to see semiconductors on this. This conductor has conduction electrons and it conducts electricity. That's really all you need now. And in an insulator, it has the electrons don't move around very easily. And then examples of a conductor are metals. Examples of an insulator, you know, plastic, rubber, wood. Agree? Oh yeah, we did this in one of the classes. I guess it wasn't yours. So all you really need to know is what is a proton? Is it positive or negative or zero charge? It's positive charge. So the net charge of this proton has to be 1e. That's the fundamental unit of charge. Now it's made up of quarks, and I need to find some combination of those quarks that gives me 1e. And it's going to be u up, up, down. That's plus 2/3. This pen's terrible. Plus 2/3. Because that's 4/3, right? Minus 4/3, or minus 1/3. So 4/3 minus 1/3 is 3/3, which is 1e. Okay? What else? These are all great questions. They're good ones for the test coming up. I think there's a question like 15. I'm not sure. I'm pretty sure. I like these questions. So I'm pretty sure I put one on, and students are often confused about it. So let's think about it. So I have this configuration of charges, and we've done variations of this, where what is the field, or what is the potential, or whatever, at these various points. Which of these points has an electric field equal to 0? which point has an electric field equal to 0? Now, if you just don't know right off, you just pick a point and start drawing vectors. And so, for example, let's pick C as an example. At C, the electric field due to this charge is going to be in that direction. And the electric field due to this charge is in that direction. So that would also be true for B and D, that the electric field due to those charges are going to be to the right. So it can never be 0 at those sides, in the middle, in between those two charges. At point E, the electric field due to this charge is going to be in this direction because it's attractive. If I were to put a positive charge at E, it would be attracted to that negative charge. And the electric field due to the plus 2q would be in this direction. Now notice that I drew that second vector a lot smaller because it's due to the smaller charge and I'm farther away from that smaller charge. So if I draw it for A, the electric field due to the plus 2q is in that direction. Due to the minus 4q, it's in that direction. Notice now that I drew this vector a bit smaller than I drew it over here. This was the electric field due to the minus 4q. The reason is the charge is still big, but I'm further away from it. So at this point over here, I'm farther away from the big charge, so my electric field due to that bigger charge is minimized. We've had variations of this that we worked in class. You see them, sometimes it's 2 positive charges or 2 negative charges, and sometimes there are problems about the force too, where you have to have 3 charges. But they all work out the same way. Just imagine a scenario for each of the points, and then figure out where is it that the 2 vectors are possibly canceled out. Usually it means that you have to get away from the bigger charge to minimize that force or that electric field. Because the bigger charge, it contributes more to the force or the field, and so you get away from it in order to make it smaller, make it more like the smaller charge. Okay? Is that clear? I'm pretty sure I have one like that. Oh, what about this one? Which direction will the beam move if it goes through these charged plates? I have positive and negative charges on these plates. This is common in like a mass spectrometer. It's common in your inkjet printer. This is how your inkjet printer works. They have little charged drops of ink that move through an electric field. And they direct the inkjets one direction or another onto your paper. This is how the old CRT televisions work. You probably didn't have those, but we had one. It was like a big old thing in a big wooden cabinet, and it didn't work at the time. You had to bang on the top of it to get it to work. Did y'all ever have one of those? Huh? Yeah, you have to get up and push the button. You too? Yeah. That's why people had kids back then, to make them change the TV station. All right, so what is the direction of the electron beam? What's it going to do? Up, down? You're right, it's going to go up. It's going to be attracted to those positive charges. In fact, if I were to draw the electric field would look like that. But the negative charges are going to feel a force that's opposite the electric field. And so they're going to move like that. We'll see that again in chapter 5 or 6. Because the electric field always runs from positive to negative. It always starts at positive charges and always goes to negative charges. And so the electric field goes up, and the negative charge feels a force that's opposite the electric field. Okay? Show you one other thing. Have one of those here. There we go. Just stretching? Okay. I want this pen back. No. Sorry. So here I want to know what is the magnitude of the charge on Q1. And y'all say that's easy, right? We've done this before. Q2 has a charge of 4 coulombs. Then what is Q1? Well, I got 1, 2, 3, 4 lines over here. 1, 2, 3, 4, 5, 6 lines over here. So it's going to be 6 coulombs. It's positive because it's coming out. Well, let me show you, what if you don't have such an easy ratio? The way you would actually calculate this is that I would take the ratio of the lines. I have 6 lines over 4 lines to the ratio of the charges, Q1 over Q2. And since Q1 is equal to 6, that means Q2 is equal to 4. But what if Q1 was not equal to 6? What if Q1 was equal to, I don't know, 8 or whatever? And if Q1 was equal to 8, well, I got 8 coulombs, but 6 lines, right? That is, it's not an integer value, but you use the ratio of the lines. The ratio of the field lines from charge to charge is equal to the ratio of the charges. So if I told you here that Q1 had a magnitude of 8 coulombs, then to calculate Q2, I would say 6 over 4 is equal to 8 divided by Q2. And 8 times 4 is 32, so it's Q2 would be 32 divided by 6. Which is 16 over 3, 5 point something coulombs. Is that clear what I'm saying? That you have to count the lines so it all works out the same, but it's not an integer value. You have to take the ratio in order to find the charge. It's nothing new. We've been doing that. It's just, it's a little more complicated when it's not an integer value. Okay? Yeah, Emma?
Could you make the ratio, the charge to the lines equals the other charge to the lines that are coming out?
How would that look?
So like it would be Q2 over 4 equals Q1 over 6.
No, you'd have to do Q2 over the lines coming out of Q1. Oh, don't do that. All right, just do it this way. The ratio of the charges, the ratio of the lines, they're equal. Okay? That one? Mm-hmm. On this one? Okay, what is the potential at point P? You're going to have one like this, right? It shouldn't be a surprise, I told you. The potential at point P, first of all, be glad that it's not electric field or forces, because this is a lot easier to do potential. I say, let's call this Q1, and we'll call this Q2. And so the potential is going to equal to V1 plus V2. V1 is K Q1 over R1, and V2 is K Q2 over R2. So that's 9 times 10 to the 9th. Negative 32 times 10 to the minus 9. Sorry, this is the worst pen I've ever had. I don't know what's up. Divided by KQ divided by R, 2 meters. Plus 9 times 10 to the 9th. Q is 4 times 10 to the minus 9. Divided by the distance, which is 2 meters. So a couple of things. Notice I didn't square the distance. This is potential, KQ over R. And then I also included the sign here. When you're dealing with potential, when you're dealing with potential energy, you have to include the signs. When you're dealing with those scalar quantities, you have to include the signs, because it has a meaning with the work, having positive or negative work, not direction. And then I add those up. You get lots of cancellations. It makes it pretty easy. These go away. This goes away and makes this negative 16. So 9 times 16. That goes away. and that becomes 2. So it's 90 plus 54, 144 negative plus 18. And that's what, minus 126? You'll have to do a problem like that for sure. You'll also have to find the field and the force for those charges. Yeah, let's look. There are some other problems. Like this one, what is the field at point P? Give me just a second. I'm going to close this and reopen. I'm going to try to get my nice pen back. Okay, what is the magnitude of the electric field at point P? Oh, yes, I got it back. If I want to know the magnitude of the electric field, I imagine a positive test charge there, and I ask myself, what is the direction of the force that that positive test charge feels, and then that's the direction of the electric field. So here, my minus 32 nanocoulomb, the electric field is in that direction. And due to the plus 4 nanocoulomb, the electric field is in that direction. Hey, remember our electric field lines? If I were to draw my electric field lines for these charges, for this one, it would look like that. That blue vector is just a sample of what the electric field lines is telling us. And the electric field line for the 4 nanocoulomb charge, it's a positive charge, so the electric field comes out. So these red and blue vectors, they're really just samples of those electric field lines. All right, so redrawing those, I have that direction and that direction. I'll call this E1. I'll call this E2. We need to calculate E1. E1 is KQ over R squared. That's 9 times 10 to the 9th. Times 4 times 10 to the minus 9. Divided by 2 squared. KQ over R squared. Cancels, 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 cancels. That's equal to 9 newtons per coulomb, or 9 volts per meter. Remember, those are the same units, newtons per coulomb, volts per meter. And then you do a similar thing for E2. It's going to be equal to, well, it's going to be 81, right? How did I know it was 81? Right, yes, or not 4 times, it's not 81, 72. Minus 72, because if this is 9 newtons per coulomb for a 4 nanocoulomb charge, this is 8 times the charge. 8 times 9 is 72. But that doesn't matter, you just do this again, and you calculate that electric field, but for that different charge. And then to find the magnitude, I want to know this vector right here. I do the square root of 9 squared plus 72 squared. I just leave off the negative there because, actually, yeah, you don't even need a negative there at all. 9 squared plus 72 squared, that must be 73 newtons per coulomb. And then if you want to know the direction, this angle theta is going to be the inverse tan of opposite over adjacent. That's 72 over 9. And whatever that angle is, below the negative x-axis. What? If it was asking for electric force, it wouldn't be asking for the electric force at point P, because that doesn't make any sense. There is no electric force at point P. If I put a charge there, what if I said, what is the force on a charge at this point? When you know the electric field, watch this. Let's put a 2 coulomb charge there. What is the force? What if I pop down a 2 coulomb charge? Well, the force is just Q times E. So it'd be 2 coulombs times what I know the electric field to be, 146 newtons. Boom, right, that's easy, because if you know the electric field, it's really easy to find the force. But if you didn't know the electric field, you could calculate the force, right? You just use your Coulomb's law. Now, what's more likely is what is the electric force on this charge, right? I have 2 charges. Well, the electric force is in that direction, and I would calculate it, K QQ over R squared. It's going to be 9 times 10 to the 9th, 4 times 10 to the minus 9. You'll see that? Sort of. 32 times 10 to the minus 9. Divided by the distance, which is 2 root 2, is that what you said? Yeah. Square root of 2 root 2 squared. That's the square root of 2 squared plus 2 squared. Alright? Whatever, it's like, I don't know what that is. 3 point something. No, 4. It's 8. Whatever. Alright. Okay? So that's how you would find the force. Is that okay? What else, folks? Right. Whenever I'm talking about forces, it's only on one charge. Although this charge is going to feel like the exactly same force, but the opposite direction. Newton's third law, right? How do you feel about the exam? Do you have feelings? You can't have feelings about an exam, right? It's an exam. Feelings about your mother, about an exam. Good feelings about your mother. What else?
So with force, you don't worry about the signs either.
Right. If you forget, it's on your equation sheet, they're absolute value bars, because it's a vector quantity. You take into account those signs when you're drawing the vectors. Is that all? I will see you tomorrow. If you came in late, or if you're sitting behind Kristen on this side, make sure you drop by.